Okay, so now that we've grouped our numbers into buckets, what do we do next?
Well, then we use the axiom of choice to select one number from each bucket to be part of a new set.
Ah, okay, so now we make a new set. I think she called it S, which is one number.
From each bucket.
Yeah, one number from bucket 1. One number from bucket 1, from bucket 2. And then if they're uncountably many, I couldn't even label bucket 1, bucket 2, but we just pick one from each bucket.
Yeah.
Yeah.
Okay?
And to do that,
So now we have this new set. We don't know what's in it. We don't know what's in this set.
Okay. We don't know what's in this set. We have no idea, right, what this set is made out of.
I think she wanted to calculate its size.
Right, and we were trying to figure out, she was trying to figure out how to calculate the size, but there was one other thing she did with this bucket. Sorry, not this bucket, this set S. What did she do?
to like prove that all these were the same size.
Well, it was a trick she did. She took all the rational numbers from -1 to 1. So all rationals.
-1 to 1?
Yep. -1 to +1. Yeah, sorry about that. Take all rationals.
Alright.
So you take all rationals in this set here. And there's only countably many rational numbers in that set because there's only countably many rational numbers. Do you remember how you prove that?
Countably many rational numbers?
Yeah. Do you remember how you can prove you can count the rational numbers?
Well, you like match them with.
You like match them with the numbers from like from 0 to 1?
0 to 1 is uncountable though. Mm-hmm. You have to match them with the positive integers.
Match each of them with 1.
You sort of bend to the set. You like bend to the line of positive integers.
Yeah, well,
connect.
We'll talk about this afterwards, but there's only countably many, so that's interesting. And then she makes copies of this set by shifting by the rational numbers in here. So she takes this set and shifts it around.
Which should make it still would have the same number of elements.
It still should have the same number of elements.
It still should be the same size.
It should be the same size.
But
There's two other things. None of those sets will overlap with each other. Why?
Well, because she's shifting them over by a rational amount.
And all of these numbers are different in here.
Okay, it's not even just that they're different.
There's
something more than that about these numbers in here that causes you to get no duplicates when you shift by a rational number.
Well, you picked only.
Oh, they're irrational numbers.
Not necessarily. Remember, one of our buckets
one number
had
is rational.
So you picked one number from each of these buckets, and each of the buckets was one of the a number, and then all the numbers of it shifted over.
By rational numbers.
Yeah.
So in the beginning, we set up our original buckets where the difference inside the buckets was always a rational number. So I can't ever shift a number from this bucket by a rational number and end up in a different bucket.
No.
Okay? And when I shift a number I picked from like bucket 2, even though I'm pretty sure I can't label buckets with numbers, if I shift it by a rational number, I shift this number by a rational number, I always get a new number, right? And I can never jump from bucket to bucket.
So you'll always be.
That's why I
numbers
always.
from the same bucket.
That's why I always get a new
set.
New set.
Yeah.
And then the fourth thing was I hit all the numbers from 0 to 1 when I do this.
When you shift over by rational numbers, I guess that would make sense because that's how you created all of the buckets in the first place.
That's exactly right.
Hitting all the numbers in the buckets.
all the numbers from 0 to 1 appeared in one of these buckets. When I shift by a rational number, I'll eventually hit all the numbers in each individual bucket.
Yeah.
So then in here, I'll hit all the numbers. Okay. So now, what paradox have we found?
Well, we've hit all the numbers from -1 to 1 with the numbers from 0 to 1.
Well, actually the opposite. I've hit all the numbers from 0 to 1 for sure by shifting this around by all the rational numbers from -1 to 1. So now, when I create the union of those sets, I definitely have all the numbers from 0 to 1.
Yeah.
You just double the size. If with a union, wouldn't that be double the size?
Why do you say double?
Because we're shifting by, I guess, twice. Well, I don't know how to say this, but maybe twice as many numbers.
Oh, interesting. Okay. I see, because we started with 0 to 1 and now we're doing -1 to 1. So maybe we've got twice as many numbers. Okay.
Maybe.
But I've got a union of sets that don't overlap, and they add up to something that has a size of at least 1. But there were infinitely many of them.
So there should be. So.
And when I add up sizes of sets that don't overlap, I just add their sizes. So I have to find something that has the same size
And you.
times infinity.
So if it's 0, so if it's anything that's greater than 0, it'll be infinite. And if it's 0, it'll be 0.
Right.
So you have to find something that's 0 and non. You can't be 0, you can't be non-zero.
That's right.
So it has no size.
That's
So we
the
have this
problem.
weird paradox.
Right. So we run into this very strange paradox. And look, this is really difficult to understand. This is starting to get into math that people are only understanding like in the last 100 years. But it's pretty cool.
Yeah.
It is pretty cool. All right, so now let's quickly talk about why the rational numbers are countable and why square root of 2 is irrational.
All right.
All right?